Hey guys, Professor Calculus is here, and today in this video we're gonna see how we should use Feynman's trick of integration in any integral that you will see. We will be solving lots of examples today, so this is gonna be a very long video compared to the others. So before we go, make sure to like and subscribe. It is free, and you can always change your mind later. So what is Feynman's trick? So the definition is that we introduce a new parameter to change the form of the, this is important, the definite integrals that are not solvable otherwise, or very hard to solve. So it's about tampering and changing a form of an integral. So how do we do that? For that, to use this kind of trick, we should use the Leibniz rule of integration. Leibniz rule of integration. What is that? It says that, for example, suppose I have an integral I defined as the definite integral of a function of a of t and b of t, f of x and t with respect to x. And now suppose that I want to take the derivative with respect to t. Let me write it in this color. The derivative with respect to t of this definite integral. What am I going to do? According to the Leibniz rule of integration, my formula for taking the integral of this, the derivative of this integral is, the first term is f of x, f of b of t, t multiplied by a chain of db dt plus minus the f of a of t, t, a chain of dA dt, and plus the integral itself from a of t to b of t of, this is important, partial f, partial t f of x t a dx with respect to x. Now, right now here, it's going to be I prime, or I can write it as di dt. And for definite integrals, like the integral from 0 to infinity or 0 to 1, these two bounds are going to be 0. These two bounds are going to be constant, thus the derivatives, these derivatives are also going to be 0. Thus, these whole terms are going to vanish, and my di dt is going to be the integral from a to b of partial f of x t partial x dx. What does this partial mean? This thing right here, it means that we are taking derivative. This means that we take, let me write it this way, partial f partial t, we will take derivative considering t as a variable and others as a constant. For example, if I have, I don't know, let's say if I have f of x, x, y, and my variable is x squared plus y squared, my partial f partial x would be 2x. So this is considered a constant. But if it was taking the total derivative df dx, it would have been 2x plus 2y multiplied by a dy dx chain. So these two, the partial f partial x is not equal to df dx. They can be equal to each other only if this term here is constant for real, like constant of 3. If y, for example, was 3, these two would be equal together, but in a multivariable function like this one, these two ain't equal to each other. Thus, this we've understood how we should use and apply Leibniz rule of integration. Now, for example, let's take an example, the first example of this integral, and the first application of this rule is the integral from 0 to 1 of x to the, let's say, 3 minus 1 over ln x dx. I could have solved this integral very easily if there was no ln x here. So I can see here that if I could suppress and manipulate the inside of this integral somehow, it would have been very great. Therefore, I'm going to use a trick. I'm going to say define I of t from 0 to 1, x to the t minus 1 over natural log of x. And if I find I of 3, I'm going to be able to find the integral that I want here. So I can use and apply the Leibniz integration rule that we saw up here, and I'm going to take the derivative of this thing with respect to t. It's going to be d dt of the integral from 0 to 1 of x to the t minus 1 over ln x dx. Now, this total derivative would move inside. This I prime of t would become the integral from 0 to 1 of, and this would become a partial derivative, partial t of x to the t minus 1 over ln x dx. And thus my I prime of t is going to be the integral from 0 to 1 of x to the t times ln x over ln x, because this term is constant, this term is constant because we're taking partial derivative, and thus I can suppress these two together, the ln x's. My I prime of t would be the integral from 0 to 1 of x to the t dx. And this integral is very easy to solve. We can use the power rule, the reverse power rule, x to the t plus 1 over t plus 1, the limit from 0 to 1, and 1 to the t plus 1 over t plus 1 minus 0 to the t plus 1 over t plus 1. This is going to go down to 0. 1 to the any power is 1, so it's going to be 1 over t plus 1 I prime of t. Now that I've changed the form of this integral, I can integrate all over it once again with respect to t to obtain my I of t. So this is going to become I of t, and this is going to become natural log of t plus 1 plus some constant of integration. And this constant of integration is very important here, because our whole answer depends on what is this constant of integration. So how should we find this constant of integration? I'm going to write my integral here again, from 0 to 1 of x to the t minus 1 over ln x dx equals natural log of t plus 1 plus c. Now, I want to see what happens to find the constant of integration. I want to see what happens if my t is 0, exactly equal to 0. So, my whole thing is going to be the integral from 0 to 1 of x to the 0 minus 1 over ln x dx equal to ln of 0 plus 1 plus c. This thing right here is going to be 0 to 1 of 1 minus 1 over ln x dx. It's going to be 0 to 1 of 0 dx. The definite integral of 0 is always 0. It's going to go away, which means 0 equals ln of 1 plus c. Ln of 1 equals 0, and c equals 0. The constant of integration is 0, and thus I can finally say I of t equals ln of t plus 1, which means that the integral from 0 to 1 x to the t minus 1 over ln x dx has another form of ln of t plus 1 if it is transformed. And notice that I wanted to find the integral from 0 to 1 of x to the 3 minus 1 over ln x dx. And if I put 3 for both of them, it's going to be ln of 3 plus 1, which is ln of 4. Thus, we found that the integral from 0 to 1 of x to the 3 minus 1 over ln x dx equals natural log of 4. And we've done this by integrating and manipulating the form of this integral to change this form into rational and more understandable form by removing this natural log of x, by considering this a multivariable function, and with differentiating, this ln x would disappear. Now let's move to the second example. I will solve as many examples as I can, and our second example is the integral of, it's a little bit harder, but from 0 to infinity of sine x over x dx. So you might think that you could use trig substitution, integration by parts, power rule, or whatever, but this integral actually does not have any closed form that we can use. Thus we need to change the form of this integral a little. You notice that we could have solved it if there was no x in here, and you might think that we can introduce a new parameter from 0 to infinity and say it's going to be sine of xt over x dx. And if I differentiate, I'm going to have a partial derivative with respect to t here, sine of xt over x dx, which means that I prime of t of mine would be the integral from 0 to infinity of cosine of xt over x times x dx. And my integral would be 0 to infinity of cosine xt dx. But there is a little bit of a problem. We can solve this integral, but you see that these bounds, because it's in infinity, it goes to infinity, it really doesn't converge to a value that we want. It diverges. But that doesn't mean that this integral as a whole is going to diverge. So we're using a wrong parameterization. So I should put parameter in another location of this integral. So this solution is wrong. This does indeed converge. You can go and verify it. So I can, how else I can suppress x here? If you look closely, you can see that if I introduce a new parameter e to the negative tx sine x over x dx, and I take the derivative of this partially with respect to t, I'm going to be able to suppress this x in the denominator. So I'm going to do that. I'm going to say I prime of t equals the d dt, sorry, you should have partial t of the integral from 0 to infinity of e to the negative tx sine x over x dx. So let me drink some water, I'm thirsty a little. Okay, good. Now, if I take the derivative partially with respect to t here, my I prime of t is going to be the integral from 0 to infinity negative x e to the negative tx sine x over x dx. And my x and this x here, I'm going to cancel away, which means that my I prime of t is the integral from 0 to infinity of negative e to the negative tx sine x dx. Now this integral is really easy to solve. You can use integration by parts. Integration by parts says that if I have the integral, for example, u dv, I can write this as uv minus v du, obviously with considering the bounds as well. Now I can say here that u equals negative e to the negative t x, and dv is sine x dx. The antiderivative of sine x is negative cosine x, because if you take the derivative of cosine x, you're going to get sine x. Now I can do this here. I prime of t is going to be u, which is negative e to the negative tx cosine x, the limit from 0 to infinity minus the integral from 0 to infinity du, or du is t e to the negative tx dt. So it is t e to the negative tx times negative cosine x dx. You calculate this limit here, you'll see that I'm going to be having e to the negative infinity cosine of infinity minus e to the 0 cosine of 0. And because cosine of 0 is 1 and e to the 0 is 1, this is going to be 1. E to the negative infinity, the limit is 0, it decays. So I can safely say that this whole thing here equals to negative 1 minus, sorry, plus t, the integral from 0 to infinity of e to the negative tx cosine x dx, my I prime of t. So let me write it here more clean. Negative 1 plus t, the integral from 0 to infinity of e to the negative tx cosine x dx. Now I can do the integration by parts again here. I can say that my u is e to the negative tx and du is negative t e to the negative tx dx, and my dv is cosine x dx, thus my v is sine x dx. So if I do this whole thing all over again, the integration by parts is going to be negative 1 plus t times the u here is e to the negative tx. dv here is sine x, the limit from 0 to infinity, minus the integral from 0 to infinity of 0 to infinity of negative t e to the negative tx sine x dx. This limit here, you can go ahead and verify that this is indeed equal to 0. Thus I can suppress it here. And I prime of t here is negative 1 plus t, the integral from the integral of negative t, the integral from 0 to infinity of e to the negative tx sine x dx. And you might notice that this thing right here is the same thing that we had as our I prime of t. Thus I can say that my I prime of t is negative 1 plus t times negative t I prime of t, and my I prime of t is negative 1 minus t squared I prime of t, and I prime of t plus t squared I prime of t is negative 1, and my I prime of t is going to be negative 1 over 1 plus t squared. Now, if I integrate all over this again, the integral of this one is negative arctan of x, because derivative of arctan of x is this one, negative arctan of x. So negative arctan of t, sorry, I meant to say t, plus c, some constant of integration. Now, this constant here is very important. It is more important than the previous ones. Thus, I'm going to be needing to find this constant using some limits. So I'm going to write this integral again, e to the negative tx sine x over x dx equal to negative arctan of t plus c. Now I want to see what happens if I take the limit as t approaches infinity. If I do that, I'm going to get the integral from 0 to infinity of e to the negative infinity sine x over x dx equals to negative arctan of infinity plus c. So e to the negative infinity is 0, and the definite integral of 0 is 0, and arctan of infinity is pi over 2. You can go and verify it graphically, and thus c minus pi over 2 equals 0. I can say c equals to pi over 2. Now, thus my integral in full form is pi over 2 minus arctan of t. And if I plug in I of 0, I'm going to get the integral from 0 to infinity. This is going to go down to 1. Sine x over x dx equals to pi over 2 minus arctan of 0, which is 0. And thus, the integral from 0 to infinity of sine x over x dx is pi over 2 exactly. And if you wanted, since this is an even function, if you wanted to have the integral from negative infinity to infinity of sine x over x dx, you just multiply this by 2 and you're going to get pi. So this is how you can use the Feynman's trick to solve the sine x integral over x. Now let's move into another example. This was a question from Berkeley's math competition, and that is the integral from 0 to pi over 2 of x cotangent x dx, or 0 to pi over 2 of x over tan x dx. Yeah, I just drank some water. I was thirsty. Just explaining all things all over. So, for this one, how should I introduce my parameter? How should I do it? I'm just going to remind a new thing here, that I can write x as arctangent of tangent of x. And here I can use this definition to say this integral is indeed equal to arctangent of tan x over tangent of x dx. Now I'm going to introduce a parameter of I of a 0 to pi over 2 of arctangent of a tan x over tangent of x dx. And if I find I of 1, the integral from 0 to pi over 2 of arctangent of tan x over tan x, I'm going to get. Thus I should change the form of this integral to be able to find I of 1. Now, if I take the derivative of this one, I'm going to get the integral from 0 to pi over 2 of the partial a, of this thing right here, arc tan of a tan x over tan x dx. My I prime of a is going to be, if I take this integral, if I take this, calculate this partial derivative, it's going to be 1 over tan x times, according to the chain rule, 1 plus a squared tan squared x multiplied by the chain inside the integral, tan x dx. And these tan x's can be suppressed together. Thus my I prime of a is the integral from 0 to pi over 2 of dx over 1 plus a squared tan squared x. Now what I'm going to do, I'm going to multiply and divide this thing by secant squared x, sec squared x, 1 plus a squared tan squared x dx. And the reason for doing that is I want to use a variable substitution. I want to say t equals to tan x, and thus dt is secant squared x dx. And my bounds here, when x equals pi over 2, t is going to be infinity because tangent of pi over 2 is infinity. And when x equals 0, my t is also 0. And thus, I gotta remind you also of this secant squared x identity, which is tan squared x plus 1. Thus I'm going to change the form of this integral a little. Thus I prime of a is the integral from 0 to pi over 2 secant squared x over 1 plus tan squared x over 1 plus a squared tan squared x dx. So if I use this variable substitution here in this one, I'm gonna get I prime of a equals the integral from 0 to pi over 2 of this is gonna be dt. This is gonna be 1 plus t squared. Sorry, I forgot to make this to infinity, of 1 plus t squared a squared. And let me write it more cleanly here. The integral from 0 to infinity of dt over 1 plus t squared 1 plus t squared a squared here. So to proceed further, I'm going to be needing to split this integral into two sections. My ansatz, my suppositions, is going to be a over 1 plus t squared plus b over 1 plus t squared a squared, which should be equal to, at last, 1 plus t squared over 1 plus t squared a squared. So, if I try to solve for a and b, I'm going to get a times 1 plus t squared a squared plus b times 1 plus t squared, which is a plus a t squared a squared plus b plus bt squared equals to 1. And if I factor out the t's together, it's going to be t squared times a squared plus b plus a plus b equals to 1. Now, I don't have a t squared term. I don't have a t squared term in here, and I only got 1. Thus, this t squared coefficient should be 0. Thus, I can say that a squared plus b equals 0 and b equals negative a squared, and this thing should be equal to 1. A plus b equals 1. And b is 1 minus a. If I equate these to each other, 1 minus a equals negative a squared. A minus 1 equals a squared. And a squared plus, minus a equals negative 1. A minus a squared equals 1. A 1 minus a squared equals 1. A equals 1 over 1 minus a squared. And now, my b here is going to be negative a squared over 1 minus a squared. So, my I prime of a, if I do the fractional decomposition, I'm going to get getting, so let me see what happens. Okay, 1 over 1 minus a squared, 1 plus dt squared dt, plus the integral from 0 to infinity of negative a squared over 1 minus a squared, 1 plus a squared t squared dt. And I prime of a is equal to 1 over 1 minus a squared, the integral from 0 to pi over 2, 1 over 1 plus t squared dt, minus a squared over 1 minus a squared, the integral from 0 to infinity of 1 over 1 plus a squared t squared dt. This should have been infinity as well. So this integral is, as you already know from the previous one, is arctangent of t from 0 to pi over 2 minus a squared over 1 minus a squared times this integral is 1 over a arctangent of at, the limit from 0 to infinity. Arctan of 0 is 0 and arctan of infinity is pi over 2. Thus I can say I prime of a of mine is pi over 2 times 1 minus a squared minus a squared 1 minus a squared times pi over 2a. And these two a's are going to go away, and I prime of a of mine is pi over 2 times 1 minus a squared minus pi a over this thing right here. And I prime of a is going to be, if I factorize pi, 1 minus a over 2 times 1 minus a, 1 plus a. I prime of a is going to be pi over 2 times 1 over 1 plus a. And if I integrate it, I of a is going to be pi over 2 integral of 1 over 1 plus a dA. And I of a is pi over 2 ln of 1 plus a plus c. You can go and use the same limit that we got, and let a be equal to 0. You'll find out that c equals 0. Thus, I of a equals pi over 2 ln of 1 plus a. And we said that I of a equals 0 to pi over 2 of arctan of a tan x over x dx equals pi over 2 ln of 1 plus a. And if a equals to 1, we're going to get 0 to pi over 2 of x cotangent x dx equals to pi over 2 ln of 1 plus 1 is 2. Thus, this is the final solution of our final closed form solution of our integral right here. We're going to stop right here. Hope you enjoyed this video. If yes, please let me know if you want the next video following the more examples of Feynman's trick of integration or not. Make sure to like and subscribe, and I'll see you next video.